Well, thank you very much. It's for me, it's a pleasure and an honor to be talking to all of you today. Uh, and I certainly realize that for a lot of you, these are very difficult circumstances, and I'm very happy that scientific discourse is continuing nevertheless. So I'm going to talk to you today about the revolutionary changes that have happened just recently in the modern metric system. I am a part of the National Institute of Standards and Technology. This is the National Metrology Laboratory of the United States. Most industrial countries, including Ukraine, have metrology institutes. The Ukrainian Institute is the National Scientific Center Institute of Metrology, the sister organization to my organization, the National Institute of Standards and Technology. And at that institute, I'm a member of the Laser Cooling and Trapping Group. Gretchen Campbell is my group leader, and these other people are the permanent members of the group with whom it's a pleasure to work on a daily basis. This talk is also coming to you under the sponsorship of the International Union of Pure and Applied Physics, and as a member of the commission that has to do with standards and constants, I'm spreading the word about the changes that have happened in the metric system. Before I start, and because it's hard to avoid thinking about this, I'd just like to say a few words about the war. As the U.S. Secretary of State has said, the United States and our allies and our partners are united in the face of the Russian aggression, and we will continue to stand with Ukraine as it fights for its future. I'd like to say that I personally am outraged by the aggression of Russia. I'm sickened by the action of the Russian soldiers, and I'm heartbroken about the effects of the war on the people of Ukraine. The resolve and the bravery of the Ukrainian people is an inspiration to me, and I believe to all freedom-loving people in the world. And I'm happy that the United States and other countries have supported the Ukrainian people in their brave struggle against the Russian invaders. And I hope that we, that is the United States and others, will continue with even more support and even more rapidly delivered. I live in an apartment building, and if you walk along the hallways of that apartment building, you'll see many people have Ukrainian flags and sunflowers displayed to emphasize the solidarity with the people of Ukraine. I'd also like to encourage you to think of questions as we go along. Put the questions into the chat, and I will try to answer them at the end. So let's get on with the talk. The revolutionary quantum reform of the modern metric system. So why are we talking about this? Well, people have said that science is about what you can measure. And in order to measure things, we have to have units. We have to have some reference system. And by international agreement, the scientific community uses what we informally call the metric system. And formally, it's known as the International System of Units, or in French, the international diplomatic language at the time that this was adopted, the Système International d'Unité, or the SI. The metric system came into being at the time of the French Revolution, at the end of the 18th century. And now in the 20th century, just a few years ago, on the 20th of May, 2019, the 20th of May being the anniversary of the international agreement that established the metric system as the worldwide metric, the worldwide standard of measurement. On the 20th of May, 2019, we experienced the greatest revolution in measurement units since the French Revolution. The nature of that revolution is a change to this international system of units, which expresses all physical quantities in terms of the 7 base units. So you're probably familiar with most of these. Mass is expressed in kilograms, length is expressed in meters, time in seconds, electric current in amperes, thermodynamic temperature in kelvins, quantity of matter in moles, and luminous intensity in candelas. And the nature of the change that we have just experienced is that today, every one of those base units is now defined by fixing the value of constants of nature. In the past, things like the meter were defined by having an artifact, a meter bar, and saying that a meter was the distance between two scratches on that meter bar. But today, the meter is defined by defining the speed of light. Now, in order to understand how it can be possible to define a unit like the meter or the second by defining a fundamental constant, I want to, and with apologies to the late great Stephen Hawking, bring you my version of a brief history of time. Since people started to talk about seconds, we have thought of the second as being a certain fraction of a day. A day is 24 hours, an hour is 60 minutes, a minute has 60 seconds. So a second, by definition, was 1 day divided by 86,400. Now, the trouble with this definition, which seems very clear, is that the length of the day is changing all the time. We've known this for a long time. Since around 1900, we have had mechanical clocks that could monitor the changing of the day. Why does the day change? Well, one of the reasons is the tides. The tides make the rotation of the Earth slow down, and this is something that's been happening for as long as people have thought about time, and even longer. Today, we have atomic clocks. Here's a picture of one of the first atomic clocks made at the England's National Metrology Laboratory. And these atomic clocks work on the following principle. Imagine an atom that has a nucleus and an electron. This might be a cesium atom where it has one valence electron. And there's a different energy depending upon the relative orientation of the electron spin relative to the nuclear spin. Now, I'm really giving you a very simplified version of this, but in order to make a transition between those two energy states, you shine in microwaves. And in the case of cesium atoms, those microwaves are at a frequency of a little bit more than 9 gigahertz. And when the frequency is just right, then this electron will flip. And you can tell that it did. And if the frequency is not just right, then the atom does not change its state. So the basic idea of an atomic clock is to have a source of microwaves, tune the frequency until the electrons flip, and then you know that the frequency is just right, namely this number. And in fact, that number is what defines what we mean by a second. So this is now the idea of atomic time. This is the new definition, the current definition of what a second is. That is the duration of 9 billion and some periods of the radiation that corresponds to this transition between these two states in the cesium atom. And since that atomic clocks were first made, and since the redefinition of the second, the performance of these clocks has gotten better and better, so that by around 1990, these clocks were good to about a part in 10 to the 14. Now, you might think a part in 10 to the 14 is incredibly good, and it is. In fact, time is one of the things that we measure best of all physical quantities. But the fact is that we wanted to do better. And the performance of these cesium clocks stalled at a bit better than a part in 10 to the 14, mainly because of the fact that the cesium atoms at some given temperature were moving very fast, more than 100 meters per second. And it's hard to measure something that's moving very fast. Most of my career has been spent developing techniques to make the atoms move more slowly. Those techniques are called laser cooling. We use lasers to slow down the thermal motion of atoms, and in particular of cesium atoms. And when we did that, when we made atomic clocks using laser-cooled cesium atoms, cooled down to temperatures on the order of 1/1,000,000th of a degree above absolute zero, we now have clocks that are good to a part in 10 to the 16. And this shows the continued improvement in these atomic clocks. And here's a picture of one of those atomic clocks at our NIST laboratories in Boulder, Colorado. And this clock, developed by Don Meekhoff and Steve Jeffords, is good to a few parts in 10 to the 16. And it's still the most accurately measured quantity in the International System of Units. But the reason I've told you this story is to illustrate a key concept, that we started with something that was rather arbitrary, namely the rotation of the Earth, something that could change for any number of reasons, not just tides, but changing ocean currents, earthquakes change the rotation of the Earth. In other words, it's not something that we can expect to be a constant, and it's something that is quite arbitrary. We've replaced that definition of time as being a fraction of the mean solar day with a definition that is based upon a constant of nature, the properties of an atom, the frequency of a quantum transition in some atom. So this is a key feature of the way in which metrology has been developed since its beginnings, that we start with something that's rather arbitrary, like an artifact, and we have changed to something that is fixed and universal, like the property of an atom. Now I'd like to tell you another story, a short history of length. Time was pretty important in historical times, but length was really important because it involved commerce. People sold things according to how long they were, like fabric. It was important in construction. When you build a building, you better know how long to make some part of that building to make everything fit together properly. The earliest standards of length were based on the human body. A foot was the length of a foot. A fathom was the length of the arm span. A cubit was the distance between the elbow and the tip of the finger. Now, this was really convenient because it meant that you always had your standards of length with you, but it wasn't very consistent. You might buy fabric from a short fabric merchant and not get as much fabric as you had expected. Well, one solution to this problem was to use a particular body, typically the body of the king or the monarch. In the case of ancient Egypt, it was the pharaoh. And in ancient Egypt, that's exactly what they did. They defined what they called the royal cubit to be based on the length of the pharaoh's arm. Now, the trouble with that was that the pharaoh was not generally available if you needed to make measurements out in the field, let's say when you were building the pyramids. And so what they did was they made an artifact. They made a royal cubit out of stone. So the length of this royal cubit was calibrated against the pharaoh, and then it became the standard of length for all of Egypt. And people who were out in the field building things like the pyramids had wooden standards that needed to be calibrated against the stone standard on a regular basis. They had to be recalibrated every month. And from the records that we know, the penalty for not recalibrating your standards was the death penalty. So these people were quite serious about their metrology, and it paid off. The baselines of the pyramids are consistent in one case to a small fraction of a percent. They're square to 12 arc seconds. These are really good, and it's because they were serious about metrology. Now, this idea of having artifacts spread throughout Europe, different towns often had different standards of measurement. Here is someone comparing their fathom arm span to the standard fathom in the town of Regensburg. This looks like it would be a good place to buy fabric because the standard fathom is quite long there. But if you were to go to a surrounding town in Bavaria, you would have a completely different standard of length. And this was a problem that was annoying, but quite common. In fact, it was said that at the time of the French Revolution, there were 100,000 different units of measure throughout the country of France. Well, the French revolutionaries decided they would fix this. And they decided to come up with a new unit of measure that they called the meter. And the meter would be defined to be 1/10,000,000th of the distance between the pole, the North Pole, and the equator along a meridian line that runs through Paris. The idea being that basing it on the Earth would make it universally available to everybody. So the reform spirit of the French Revolution was in line with this idea that there should be a uniform and universal standard that would be available for all time and for all people. And in fact, this medal that was cast in commemoration of this idea shows a mythological creature actually measuring the Earth. Now, that's in fact what they actually did. They sent out surveyors from Paris to measure the length of the meridian going through Paris along a line going from Dunkirk in the north to Barcelona in the south. And those surveyors, who spent 6 or 7 years doing this job, returned to Paris with their results, showing what the measurement of that distance was in the old units, and used that to define what was meant by a meter. Now, the trouble is, of course, it's not very easy to continually be measuring the Earth. It took these guys 6 years to do it, and it was in the middle of a war, so it was not very easy. And so what they did was they made an artifact, just like the ancient Egyptians did. This is a picture of that artifact. It's made out of platinum, and it was deposited in 1799 in the archives of France and became the national standard for the country of France. Now, as time went on, more and more countries adopted the idea of the meter as their standard of length. And in 1875, there was an international meeting, the Convention de Mètres, which 17 nations of the world agreed to adopt the metric system. The United States was one of them, by the way. And as part of this, they agreed to the establishment of an international body, the International Bureau of Weights and Measures, who would make a new standard. The new meter, called the International Prototype of the Meter, was made so that the length between two scratches on this bar were as close as possible to the end-to-end length of the meter of the archives. And this became the standard of length for the entire world in something like 1889. Now, the trouble is that almost as soon as this meter bar was made, it became obsolete because of the fact that people of the time were building optical interferometers. Albert Michelson, who later got a Nobel Prize for this sort of work and is famous for having measured the speed of light, designed this interferometer in which light from a lamp, say a lamp of cadmium, would come in, hit a beam splitter. Some of the light would be transmitted to another mirror. Some of the light would be reflected to another movable mirror. And the reflection from these two mirrors would be combined again on this beam splitter and produce an interference pattern, which you see here, or a nicer version of the one that you see here. Now, when the two beams of light, the one from the movable mirror and the one from the fixed mirror, combine, because they are waves, they can combine so that they increase the strength of the wave, or they can be combined in such a way that they cancel it out. And if they cancel it out, then you get a dark spot. And moving this mirror by just a quarter of a wavelength of light, which is a couple of 100 nanometers, a few tenths of 1 micrometer, will change this spot from being dark to bright. Now think about this. You have a meter stick that has a scratch on it. That scratch is 20 to 30 microns wide, and you're looking at it with a microscope that has a resolution of 1 micron. You can do incredibly well, but this interferometer can do even better. And so people started to use interferometers and the wavelength of light as a kind of de facto standard of the meter. Finally, in 1960, the definition was changed. The definition was changed so that the meter was a certain number of wavelengths of the light from a krypton lamp which is pictured here. Krypton being a noble gas, you can run an electric discharge, it produces an orange light, and the wavelength of that orange light became the new definition of the meter. But it didn't take long, because 1960 was the year and the laser was invented. It didn't take long before people had lasers whose light was much more pure than the light from a krypton lamp. And so by the 1970s, almost everyone was using lasers like this as, again, a de facto standard of length, not the official definition of length as prescribed by the International System of Units, but a better standard because the technology of these lasers was better than the lamps that were used to define a meter. And so it seemed obvious that one needed to redefine what one means by a meter. The obvious choice would have been to redefine the meter in terms of these wonderful lasers, these iodine stabilized helium neon lasers. But fortunately, people did not take the obvious choice. They took what I consider to be a brilliant choice. They defined the speed of light. Now, why does this allow you to define the meter? Well, we have this general rule that the wavelength of light times its frequency is equal to the speed of light. People had learned by 1983 how to measure the frequency of light. And they realized that if they defined the speed of light, then that meant that if you could measure the frequency, you would immediately know what the wavelength of the light was, regardless of what kind of light it was. And the new definition of the meter then was that it was the length of path traveled by light during a time of some fraction of a second. And this fraction, this number here, is now the defined value of the speed of light in meters per second. Now, the beauty of this measurement, the beauty of this definition is that if somebody figures out a better way of measuring the frequency of light, and they did, or if somebody figures out a better way of making a laser that has a more stable frequency, and they did, then this definition already takes care of that. We don't need to change the definition because this definition incorporates all possible improvements in lasers and frequency measurements. Well, I said people did make those kinds of improvements. Here are two of the people that did, Jan Hall and Ted Hench, who got the Nobel Prize in 2005 for their work on measuring the frequency of light and for making better lasers. And so it was exactly as hoped. All of these improvements were already incorporated into the definition. So now we have an even better way of defining a unit. We started with an artifact, just as we did with the case of the second. This artifact was a meter bar, and we went to a constant of nature, something unchanging, a particular atom. But as time went on, it turns out other atoms were better. And the new definition then was to define the meter in terms of a fundamental constant of nature, namely the speed of light. And the beauty of this is that there should never be need to change this in the future. So the definition of the meter is both brilliant and beautiful, even more beautiful than the definition of the second. And on the 20th of May, the international metrology community brought this beauty to the kilogram, and for that matter, to the ampere, the Kelvin, and the mole. Well, why was it necessary to do this, and how was it done? Well, in order to tell you about that, I'd like to bring you a light history of mass. Just as in the case of meters, and there were artifacts in ancient times. This is a set of polished stones that was the standard of mass for ancient Babylon. And elsewhere, there were similar manufactured objects, which were the weight standard or the mass standard of those various places. Now, at the time of the French Revolution, the revolutionary reformers wanted to make a universal standard of mass, something that would be good for all time and for all people. And so, using the philosophy that the meter which was supposed to be the measure of all things, could be used, they defined a new mass standard, the kilogram. They defined it to be the mass of 1 cubic decimeter, what we call a liter, of water. So if you had a cube of water, 1/10 of a meter on a side, the mass of that water was defined to be a kilogram. Now, it turned out not to be so easy to get, excuse me, exactly 1 liter of water. And for that matter, water expands and contracts with temperature, so that makes it harder to determine what a kilogram is by this definition. And so they did what so many people have done in the past. They made an artifact. And here is a picture of me holding that artifact. This is the kilogram of the archives, made out of platinum. You can see it's rather small. Platinum is very dense, so you don't have to have very much of it in volume to make a kilogram. And this kilogram, made as close as possible to the definition based on it being a liter of water, this kilogram was deposited in the archives of France in 1799, and it became the standard of mass for the country of France. And as I said, other countries adopted the metric system. And so at the time of the Convention du Mètre in 1875, it was agreed that there should be a new prototype kilogram. And some years later, in the 1880s, a new kilogram was made. You can see it inside these 3 glass domes. And it was made as close as possible to the mass of the kilogram of the archives. And that became the international standard for the entire world. For up until just a few years ago, this defined what was meant by mass for the entire world. Now think about this. In the 21st century, where we are now, the unit of mass is an artifact, or it was a few years ago, a piece of metal that was made in the 19th century based on an object made in the 18th century. I consider to be this definition to be scandalous. Imagine if somebody had left a fingerprint on the international prototype of the kilogram. Every one of us in the rest of the world would lose weight. Well, that's just intolerable. Well, nobody has left a fingerprint on the international prototype kilogram. They're much more careful than that. But for reasons that we don't understand, the mass appears to be changing. Here is a plot of the mass of a number of copies that were made at the same time that the international prototype kilogram was made, and looking at the comparison of those copies to the international prototype kilogram. And they're all changing. And they're mostly changing in the same direction. Well, when you see something like that, you might think, well, probably the international prototype of the kilogram is changing as well. Maybe all of these things are changing. But of course, by definition, the international prototype kilogram cannot change because it is, by definition, a kilogram. Well, that's intolerable, and we have to fix the problem. And the way we fix it is going to be the same way that we fixed the meter problem. We're going to define a physical quantity, I mean, a physical constant of nature. And for the meter, that constant was the speed of light. What are we going to use for the kilogram? Well, to give you an idea of how that works, let me remind you of what is probably the most famous equation in history, E equals mc squared. What does that mean? It means that the energy of an object at rest is equal to the rest mass of that object times the square of the speed of light. Now, there's another equation that's not quite as famous. It says that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now, remember, we know how to measure frequency, and we've defined the speed of light. So that if we combine these two equations together and solve for the mass, we find that the mass, and what does this mean? It means that if I had a particle that emitted a photon of frequency f, that its mass would change by this quantity, Planck's constant times the frequency divided by the speed of light squared. Now, you see what this means is that if we define Planck's constant, if we measure the frequency, We've already defined the speed of light. It tells us what the mass change is in kilograms, and that gives us a way of defining what we mean by a kilogram. Now, we don't actually measure the weight of photons. We could, and we do, but not well enough. There's a new idea due to this guy, Brian Kibble, who invented an electromechanical device known as Kibble Balance. And here's um, a movie that shows you how it works. So first, I want to remind you of the standard way in which we weigh things. We weigh things by putting them on a balance. We take an unknown weight and we add known weights to the other side. And when the balance balances, then we know what the weight of the unknown weight is. That's the way we always measure things, how we weigh things. Now, I want to invite you to imagine a different way of doing things. Take a coil of wire and put current in it, and put it in the field of some permanent magnets. A wire in a magnetic field will feel a force on it, and we can calculate what that force is based on knowing the current and knowing the magnetic field. Now, you have to know what the current is to a high degree of precision. And we have to know what the magnetic field is and what direction it's pointing relative to the current at every point. And that's very difficult to do. So this idea, while fine in principle, is not actually going to work. And here's where the genius of Brian Kibble comes in. What Kibble said was, okay, let's take this same coil of wire and let's take the leads of that coil of wire and connect them to a voltmeter. And then now let's move the wire in the field of that permanent magnet, and then a voltage will be induced. This is how a generator works. And if we measure the voltage and also measure the velocity of this moving coil, then we will have all the information we need to do this different measurement of mass. And so we measure the voltage, we measure the velocity when that voltage is being created, and we call this the velocity mode of measurement. The other mode is the one we've already talked about, where we put current into the coil, we put it in the same magnetic field, and that's the key thing, it has to be the same magnetic field, and we compare the force to the force of gravity of our unknown mass. Now, the beauty of this is that this unknown mass that we have times the acceleration of gravity is the force on one side of the balance. We multiply that by the velocity that we get, not from the force mode, but from the velocity mode. And we know that that's got to be equal to the current that we get from the weighing mode times the voltage that we get in the velocity mode. And if we solve for the mass, the reason why this is true is because this is mechanical power and this is electrical power. Force times velocity has to be equal to current times voltage because they're both measures of power. We solve for the mass, and that's our new definition of mass. Now, what does this have to do with Planck's constant? Well, it has to do with the fact that we can measure the current and the voltage in terms of quantum phenomena called the quantum Hall effect and the Josephson effect that give us these things in terms of Planck's constant. And since I'm running out of time, I'm going to go very briefly through this, and you can ask me questions about this later. Here's Brian Josephson and Klaus von Klitzing, who discovered the Josephson effect and the quantum Hall effect. And the point is that the Josephson effect is in terms of 2e over h, and the quantum Hall effect in terms of h over e squared, and the e's cancel out, and the mass is proportional to Planck's constant, just as I promised. Well, here's a picture of one of those Kibble balances at NIST, where I work, and these things are now being used to realize the kilogram to about a part 10 to the 8th, which is better than the changes that we were seeing due to whatever. We don't really know what was causing those changes in these other kilograms. The people who do this are really serious. They tattooed the value of Planck's constant and the other constant on their arms. And this is really a wonderful new way of measuring the kilogram. There's another way, which if you ask me about it, I'll be happy to tell you, that involves making a nearly perfect silicon sphere, knowing the mass in kilograms of each one of the identical atoms in that sphere, and essentially counting how many atoms there are. Well, when the entire world, using one of these two methods, agreed on the values that they were getting, the world got together in November of 2018 in Versailles at a meeting of the General Conference of Weights and Measures to decide by international agreement to adopt a new definition of the kilogram and of the ampere, the Kelvin and the mole, based on fundamental constants. And here, after a unanimous vote that adopted this, this new definition, here is the movie that they showed.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have es geschafft. Lo logramos.
雷西伯利，我们做到了。
Biz bundan ayrıldık.
Proud die.
Вызвали жасады. Det är som förut.
Vi сделали это.
Vi gjorde det.
Amerika dia.
Mi smo to učinili.
Dokázali jsme to.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shattere lavorisha.
Selamat sukses.
Parabéns.
Ongela. Omedeto.
Anguida.
Unexchangeable.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Well, I have to admit that I still get emotional when I see that, because the unanimous agreement by some 60 countries around the world, in spite of all kinds of differing perspectives, this is the way things ought to be done. Unprovoked assault on a neighbor is not the way things ought to be done. Well, there's many more things I could tell you. The ampere was changed, the mole and the Kelvin were changed. But the point is that we have now finally realized the dream that the French revolutionaries had of a system of units that would be good for all time and for all people. The 1875 Convention du Mètre brought us an international agreement about units. The French Revolution had given us the idea, and the Convention du Mètre made this idea international. And now on the 20th of May, the international community put into effect the agreement that they'd made some months earlier in Versailles to change the international system of units so that it truly was something that was good for all time and for all people, realizing the dream that the ancient reformers had. Except for one problem. It seems that time itself is still tied to a specific atom, namely cesium, rather than to a fundamental constant. There is the definition of the hyperfine frequency of cesium, a constant of nature, but not really a fundamental constant. And the trouble is that today we have atoms whose frequencies can be measured more accurately than the frequency of cesium. And we will probably have to change the definition of the second. So as for the future of the definition of time, only time will tell. It's the end of the talk, and I would be very happy to answer questions. I've got a number of possible questions that people might want to consider, but I'm sure that you have questions of your own, and I'll be happy to either return to any of these questions, which I'm showing very quickly, and I realize may not be very easy to read, but I'm very, very happy and pleased to take your questions now. Thank you very much.
Thank you very much for a great lecture. It was a great pleasure for us to hear today. Yeah, we have some questions. The first one is it correct that uncertainty of frequency of radiation emitted by the cesium atoms, in particular caused by a Doppler shift of frequency because of thermal motion of the atoms?
Exactly. In fact, that's one of the biggest effects is the Doppler effect. Now, people have thought of all kinds of clever ways of getting rid of the Doppler effect. So the key thing is that when you shine radiation on the cesium atom, that you have radiation going both this way and that way. And the way we guarantee that is by putting the radiation into a resonant cavity. And if that resonant cavity has a very high quality, then it means you'll have as much going this way as you have going this way. But the cavity is never perfect. So the degree to which it's not perfect is the degree to which that Doppler effect still comes in. But there's more. There's a relativistic shift. And moving clocks run slow. That's what Einstein taught us in 1905. And there's no trick to get rid of that. So the only way you can deal with it is to measure the velocities and make a correction. Another important feature is that when the atoms are moving fast, you simply don't have as long to look at them. And that means that it creates more uncertainty. You might think of it as because of the uncertainty principle. The uncertainty principle says that the uncertainty in time times the uncertainty in energy can't be any smaller than Planck's constant. And so if we have a short time, that means we have a small uncertainty in time. That gives us a larger uncertainty in energy. And all these things affect the difficulty of making measurements when the atoms are moving fast.
Thank you. The next one, they got it. Is the C based on the interregulation of the units? I mean, probably it meant about C system, I think.
Okay, so I'm not sure exactly what the question means. Before the meter was redefined, we had the old definition of the meter. And then people measured the velocity of light using that old definition of the meter and the definition of time. The best measurement that they could make at that time then became the definition of the meter. So the spirit of this is that no one should notice that you changed the definition of the meter, because we make a measurement using the best technology we have, namely the old definition of the meter. We see what the speed of light is based on that. We now define the speed of light to be exactly that value. And because the definition was within the uncertainty of the best possible measurements, no one should be able to notice. But as time goes forward and people do better and better, then we're not limited by the old definition. So I hope that answers the question, but maybe if it doesn't, maybe whoever asked it can follow up to clarify the answer.
All right, the next one, is the nano accuracy of units nowadays required practically?
So the answer to that is yes and no. It depends on what you mean by practical. So let's take time, which is the thing that we know the best. It was necessary to have really accurate atomic clocks defining what we mean by time in order to do things like scientific things like long baseline interferometry, things that allow us to do radio astronomy with very high resolution, so we can see objects in the sky in the radio domain. So there are scientific reasons for wanting really, really good clocks. Now, you might then ask, is this something that's practical? Well, if you're a scientist, it's practical. But it also turns out that high-speed communication, what's called synchronous communication, requires that the sender and the receiver have synchronized clocks so that they can sort the bit streams that are being sent along some, let's say, fiber optic transmission line. They need to be able to sort them according to who's supposed to get the information. And in order to do this in a way that is asynchronous, that is not determined by the bit stream itself, then you need good clocks at both ends. Broadcast networks need to synchronize their broadcasting, and so they need atomic clocks. And so there's both scientific and practical reasons why we need these very high quality clocks. Now, presently, we are working with atomic clocks that have potential accuracies of a part in 10 to the 18. I don't know of any reasons why we need a part in 10 to the 18 for technology, but we certainly need it for science, because we're using those clocks to ask a very important question. Do the fundamental constants of nature change with time? And these incredibly accurate clocks are giving us answers to that question. So far, the answer is no, but it's a very fundamental question. So I hope that answers the question.
Thank you. Will it be accurate to measure time by the period of rotation of a body in its orbit in vacuum?
Well, in a certain sense, the Earth is a rotating object in vacuum. The trouble is it's not isolated, because there's the moon, there's the sun, and those bodies affect its rotation. So if you were to have some other sort of a body in vacuum rotating, people have studied these things very carefully. And the trouble is that there's no such thing as isolation. First of all, there's no such thing as a perfect vacuum. For another thing, the suspension system that allows you to keep this thing spinning in vacuum isn't perfect, and it could add noise to the rotation of these bodies. So while it is possible to have such a body in the laboratory, for example, or for that matter, a celestial body, they're not truly isolated. And so they don't really make very good time standards. For example, some people have proposed that pulsars, which are rotating neutron stars, very far away, sometimes billions of light years away, could be length standard or time standards. But in fact, the way the scientific community uses these things is to compare them to atomic clocks and see how these pulsars are slowing down due to, say, emitting gravity waves. So we're using these things as laboratories to teach us something else, using the atomic clocks to provide the standards of time, using these rotating objects as a way of learning about something else.
Thank you. How we could measure the gravitational acceleration used in the mass measurement equipment?
Yes. Well, it turns out that people have developed some really wonderful ways of measuring the acceleration of gravity using interferometry. That is this way of measuring length that I told you about, that was invented in the 19th century. The idea is you take a mirror, make it part of an interferometer. If you move the mirror, you'll change that interference pattern that we talked about. Let me see if I can remind you about that. Yes. So, for example, there's this interference pattern, and you then drop the mirror, and this interference pattern is changing while the mirror is dropping in vacuum and accelerating. And if you record the passage of these fringes as a function of time, then you can fit the fringe pattern to a curve that reflects the acceleration of gravity and determine the acceleration of gravity. So this can be done to better than a part in 10 to the 8th. It can also be done by dropping atoms. So there's a device called an atomic fountain where you toss the atoms up in the vacuum and they come back down while you do spectroscopy on the atoms. And because of the Doppler shift, you can measure the acceleration of gravity. These work even better than the falling mirror. So these ways of measuring acceleration of gravity are available, and for the moment at least, they're good enough that they don't limit the ability to measure mass using these techniques.
Then the last one, how do we know constants are permanently unexchangeable?
Yeah, well, this, of course, is one of the things that we don't know for sure, and one of the things that we would like to measure better. So let me digress just a little bit and talk about the possibility of constants changing. Most people, including myself, will tell you that it only makes sense to talk about the changes with time of constants of nature if those constants of nature do not have any units. Now, what do I mean by a constant that has no units? The ratio of the mass of an electron to the mass of a proton obviously has no units. That's a pure number. The speed of light, which is how fast light goes has units. You have to express it in some units. Meters per second is the ones that we've chosen. Now, we have now defined the meter by defining the speed of light. That means that the speed of light cannot change with time because it's legally defined. It's meaningless to talk about the speed of light changing because we use it to define what we mean by a meter, and the only way we can express the speed of light is in meters per second. On the other hand, if we made some sort of a measurement that was sensitive to the ratio of the electron to proton mass, for example, the vibrational frequency of some molecule, if we measured two different molecules that were sensitive in different ways to the ratio of the electron to proton mass, then if we saw the ratio of those frequencies change, we would know that the electron to proton mass ratio had changed. Another favorite constant that is dimensionless is called the fine structure constant. It's a dimensionless measure of how strong the electromagnetic force is. By measuring the frequency of two atomic clocks that depend on the fine structure constant in different ways, we can measure whether the fine structure constant is changing. And these measurements have been done in the laboratory, and the result is that the fine structure constant does not change by as much as a part in 10 to the 18 per year. And we're trying to make these clocks better all the time so we can pin that down even better. So this is one of the most exciting areas of investigation right now, because using that same technology, we can test the theory of general relativity. Einstein told us that clocks will change their ticking frequency depending upon the gravitational potential that they're in. But he also taught us that two clocks of different sorts, as long as they don't depend on gravity for their operation, like atomic clocks, then two different clocks should maintain the same ratio as we change their position in the gravitational field. If that's not true, then what it means is that one of the most fundamental principles of physics, the equivalence principle, is wrong. And so making measurements on atomic clocks at this very high level of precision is a really important and exciting thing to do, because it might show us that one of our most treasured theories, the theory of general relativity, isn't really true. And that might point us toward how we can unify the theory of gravity and the theory of quantum mechanics, which is one of the great challenges of our current time.
All right, the last one is, tell us please about your experience in the Nobel Prize ceremony.
Well, one of the things that I was a bit surprised about with the Nobel Prize ceremony, it's not just the ceremony, there's a whole week of events. And the ceremony itself is a very I would say a very solemn sort of ceremony. It's the king and the queen and the royal family of Sweden are sitting on stage. The Academy of Science and the Academy of Literature, the members of those academies, the Academy of Medicine are sitting on stage. The Nobel laureates for that year are sitting downstage from them. There are speeches made about the nature of the work. The laureates are invited to come and receive the prize from the hands of His Majesty the King. It's all very, very solemn. But you know, a lot of the rest of the week is a real party. And I guess that was one of the things that surprised me the most, was what a wonderful celebration it was. There's an all-night party that is put on by the students that was just fantastic. It was really quite an amazing experience. One of the former Nobel laureates who came back from Stockholm told his colleagues that it was like a fairy tale. And I really felt that that's very much what it was. At dinner after the ceremony, I sat next to the Queen. And at the another dinner that was held at the Royal Palace on, I think it was the following day, I sat next to the Crown Princess. She will become the monarch of Sweden when the monarchy passes from her father to her. This was really kind of amazing for a simple person like myself to be sitting next to first the Queen and then the Crown Princess, and so it was quite an amazing and remarkable experience.
All right, thank you very much. It was a great pleasure to see you today, to talk with you. I guess that we will very soon meet in Kiev, and we'll do the in-person lecture with our participants, with our students in Kiev. And I hope that will be very soon.
I hope so too, and I will be so pleased to come to Kiev to give a lecture. And I promise to give you a lecture that is much more fun than the one that I've given today, because what I most enjoy talking about is laser cooling, which I've spent most of my career doing. I spent part of my career doing these fundamental constants, but I spent most of my career doing laser cooling, making the coldest stuff in the universe, making things that are now about a billionth of a degree above absolute zero. And I have a lecture which involves lots of live demonstrations, and it's a lot of fun.
I hope that will be very soon, I think. Thank you very much.
You're most welcome, and I look forward